Oh, you're also German, by the way?
Yeah.
Ah.
All right, guys. So welcome back to our next session with Oliver Zeigermann. So he's the Chief Visionary Officer and Software Developer at Embark Software Consulting. And by being a practitioner for more than 3 decades, he's more than a specialist, I guess, in front-end development and machine learning. And that's what he's going to talk about today. So today we have a talk about visual regression testing with neural networks. Have fun, everyone.
Okay, thanks a lot. Let's get started. As Jonas already said, I'm Oliver. I'm from Hamburg, Germany. As Jonas is also from Germany, we just noticed that. We were speaking English all the time. So I had this talk several times before, and it occurred to me that it's pretty involved. So I'm giving you the too long didn't read at the beginning, so that you at least have an idea what this is all about. So maybe then it's easier to not lose track. So if you look at it, like most people approach an application visually, that means you look at it, if you can see.
One question, Oliver, are you sharing slides right now?
Oh, sorry. I forgot to share slides. I'm looking at my slides right now. I'm very sorry, but I will do it right now. Should be okay now.
Now it works.
Okay.
All right.
You didn't miss a whole lot. So this is the first slide. So as I said, most people, they look at an application. So if you look at an application, you will typically be able to tell if something is off or not quite right. So it might be a good approach to have testing on that level as well. So visual regression testing, which is a known thing, I'm not going to talk about that a lot, is the right level to attack that. But they're pretty hard to develop, at least from my experience, and then they break pretty often. So they're brittle. So I will use autoencoders, which is a special kind of neural networks. And I will try, and I will succeed, I can give you that, to teach that neural network how an application normally should look like in general. Maybe it's just a page of an application, but we will have a look at that. And then something doesn't look normal, then that might be an indication that there's something broken on that page. So what I'm proposing is a more general approach to visual regression testing. How this is done and why that might be hard and what kind of bugs can be detected is the topic of this talk. So first, regression testing, this is what I copied from Wikipedia. I'm not reading all of it, maybe just the first line. So regression testing, sometimes called non-regression testing, is rerunning functional and non-functional tests to ensure that previously developed and tested software still performs after change. So you do something and you want to make sure, or at least want to know if you broke something while doing so. So I made this picture actually yesterday in the beer garden. I'm German, so just to give you like a broad overview, what kind of test are we talking about? And if you look at a beer glass as my metaphor for testing, that might be the beer glass itself, which I would call the static part. So it contains everything. And that static testing could be ESLint or TypeScript or whatever linter you have. Then the dynamic testing typically is just the foam on top. And the dynamic testing would be unit testing or integration testing on the code level. Then there's always a certain amount of manual testing left. And I'm saying, well, this is the hand that does it. But the most important part, I mean, all the beer, at least from my perspective, it's in the visual testing. So you click on the application, and that is the whole beer. And that's what this talk is about. So just to make sure we're on the right track, a little bit more high level. This is our sample application. As I said, I'm German, but so this is in German. Hopefully that's the only screenshot that's in German, but you can switch to English. And it's very simple. It's just a single page or single view in the application. And I'm just testing for a single view. So I guess the approach might have to be trained for each view of the application. But it's simple enough, but you can also break it in very, very interesting ways. So that might be a good thing to have an application like this. So I'm just checking for the questions. Sorry. Okay, nice. That's it. It's actually a running application. It's a little bit more complex now. As I said, you can switch languages. Not too fancy, but it should do. So visual regression testing, you probably know that it works by comparing two images, the actual image with the image that is known to be correct. And then often you have that slider in the middle here that can give you like a mean to compare the two. And maybe that's not enough. So all the visual regression testing, they also have like a means to compare that automatically, but just mostly counting the pixels that are off. And you can also display them. So like this. And then you can also set a threshold. And we will also talk about thresholds a little bit more later. You can set a threshold and you can say, if this is maybe 5% off, then I think it might be broken. And 5% actually is a lot, because a lot of applications, like I'm going back a few slides, a lot of applications like mine, they have a lot of like white pixels. So the majority of pixels are actually white. So if you compare them, I mean, even if you were displaying something completely different, you might have up to 90% of matching pixels. So 5% actually is quite a lot. 6%. And then that test fails. So this is visual regression testing. And then the question is this any good? And as I said earlier, like visual testing for me is the beer in the beer glass, like the most important part. I would say it's good. It tests at the right level. So you can have like all the unit tests passed, but you still the application isn't usable at all, or just looks really bad, and you wouldn't even notice running the test. So front end is always something that displays to the user, so it might be a good idea to do that, to test on that level. But that's the hard part. You have to create and maintain the ground truth for each like whatever setting you have in mind. You have to have an image to compare to, and that's actually pretty hard to do, and that's also very brittle. And then you also get a lot of false positives. There are only a slight variation in the way the screen is displayed. Sometimes even going from Linux to Windows or the other way around. Then the fonts might be slightly off, or I don't know, some resolutions might be different. And you would be surprised to look at this. Maybe you're surprised. You might be surprised to look at the same application in Windows Chrome or Linux Chrome. So, or maybe the shades are a little bit different. Right? You have a little bit of different styling, and then everything's broken. So that's bad. And that's because this thing is not intelligent. So if you just compare pixel by pixel, that's not intelligent. There's no idea or abstract concept of how the application should look like. But we, as a developer, we have that. So maybe we can go in that direction. So I said, like, visual testing is pretty important. What kind of errors can only be found on the visual level? So this is something like I would guess a lot of people have seen, and it's about this here. So you change a translation string, and then maybe most of the time it works well, but at certain points you have this overflow, which is ugly, which will give you the impression that's not high quality app. And sometimes, depending on how you did the styling with the CSS, this might even be cut off here, and it might be unreadable. But typically it's just ugly, but it doesn't jeopardize the usability of the application. It's just, it doesn't look good, but maybe it still works. Other kind of stuff that I mean, this is obviously constructed. I mean, there's setups, but this is a real error. So you can produce that error in my application, which I thought was pretty well tested and everything was fine. So if you get an overflow here in this box, because you have a very, very big number, for example, that's just one example. You can have all kinds of overflows, or depending on the resolution of the screen, things might break in a weird way. So you see this button here is missing now. It's missing because of that overflow, or it's not overflowing, it's just growing. And now the application is no longer usable. At least not really, because there was a minus button here, so you can click up and down the counter. It's pretty simple. So it's no longer usable. And that's a very tricky thing to find. Maybe it's even impossible, because if you knew about that situation and you had a screenshot that would, I don't know, show how it should look like, you could just as well fix the bug. I mean, it's a bug that maybe you wouldn't even call it a bug. I don't know, but that behavior has been in the application for a long time, and maybe you're just revealing it. You could do that as a human. Obviously, you see, oh, the button is missing, but how could a visual regression test find that? Not possible. Maybe because it's not even a regression, because it has been there all the time. So that's tricky. So it could be found on the visual level, but it's still tricky to do that in a classic way. So what's the challenge? You get a screenshot. How do you know if what would you expect? How should it look like? And is it possible to I don't know, tell an overflow from just a changed text? Is it possible? I mean, how's it doable? Yeah. Okay. So coming to machine learning now. So I know that is a bad drawing, but I do my best, I promise. It's just that I'm not very good at it. So in classic development, maybe you understand that. You have an idea, you analyze it. Here, people are doing this. You have some knowledge about something. Oh, this is how it works. Maybe you write down some requirements, or you just have it in your head. It doesn't matter. And then you spit out a program that does something for you. That's classic development. And there could be different roles. Maybe it's just you. It doesn't matter too much. Maybe it goes in a circle. But the important part is you start with some sort of model of the world or an idea what you're trying to do, and then you write some code. And in machine learning, that's pretty much reversed. So in machine learning, the model is on the right side. So it's the outcome of the whole thing. And you start by using data. So something that you have, whatever you have, you can start using it. Maybe you have some tabular data. We will obviously use image data, but it doesn't matter too much. So sometimes people say you don't have to have domain knowledge, but it's not quite true. But you don't have to analyze it like in too much detail. At least that's true. You start from data, and in the end, you hope you get out a model. You also need to do some more stuff, but we will get to that. And that's especially bad drawing, I have to admit. But it's still so the content is really important. So now if you decide what kind of machine learning, so there are different kinds, what kind of machine learning could you use? So if you have data, you could ask yourself, are you interested in categories? And we sort of are. Like, is it off or is it not off? So we're not interested in numbers. And then is your data labeled with categories? So do you know? I mean, if you start with the images of the screenshots of your application, you typically don't know is it right or not. If you do, then you could go the supervised classification direction, which is just normal. Or if you don't know if it's correct or not, you go in the other direction, which would be unsupervised, which is the thing that we're doing. So this is our plan. And we're using an autoencoder for that. Don't worry, this is just an overview. We will have a lot of time to go into the details. So we are formulating something, or we are making up machine learning setting, so to say. And in machine learning, you provide some data, and the input data for this sort of thing, the autoencoder, can be all kinds of data. So an image, for example. And the special thing about this autoencoder, it spits out the same thing that you feed in. So maybe I'm going quickly ahead, and you can see this image, which I took from here. So this is not my work. That's why it looks so nice, I guess. So you put something in, this 2 here. You put it through a so-called encoder, which is the first part of this thing. And now something interesting happens in the middle. You have a very, very low-dimensional compressed representation of that. And from that, you put it through a decoder, and you hope to get the same thing back. And I think maybe I'm not quite sure if you can see it from over the broadcast, but the right one is a little bit blurred because typically this doesn't work perfectly. It works quite well, but maybe not perfectly. And that's the whole idea. So you might ask, why would I do that? And the magic is in the middle here. So this bottleneck typically, maybe it's just 2 dimensions. That means 2 values, or maybe 8. So we will have 8 later. Maybe it's 100. It depends. But the important part is it is of much less dimensionality than the input. So if you say you have, I don't know, 1000 by 1000 image, you put it through this thing and you compress it to 2 values or 8, then obviously you need to have a lot of knowledge of what you were compressing there in order to decompress it again. So this thing, if you train it, it will be highly specific to the input, and that's the trick. So we will see that in a second. First, what can you do with that? So you can compress, which is not good by itself, but it's what it does. You could denoise data, which is not what we're doing. You could reduce the dimensionality of something. You put something in, like, I don't know, whatever you have, and then you reproduce it, and in the middle, the bottleneck, it has a reduced idea of what you are feeding it. And PCA, if you know that, principal component analysis, is just a special case of that. Or you could build an abstraction for further use, I don't know, maybe to actually visualize what you're seeing. So you have a lot of images, and then you are visualizing those images in the 2-dimensional plot and see maybe something is close, and you cluster for spatial similarity. Are they in a similar position? That could also be used to detect an outlier. If something is quite off somewhere else, maybe it's strange. Those are the typical ways of using an autoencoder, but we will also use a different means of doing that. Now we're coming to the main part. So we were seeing, like, a little bit introductory, what is virtual regression testing? Why is it maybe flawed or very hard to do? It would be the right level, but it's hard to do. And then also maybe a little bit rushed, what is machine learning and what can autoencoders do? But we will look at this again now. And now we are looking at combining those two. And those are the two, like, domains I've worked in the recent past, like building and testing applications, and then also doing machine learning. So we are combining them. So again, let's remind ourselves, what are we trying to do? So we have a screenshot. How do we know how it should look like? How they're supposed to look like? Or anything like that? How could we tell is it correct or not without having a reference screenshot? We as humans, often we can do that. Maybe the machine can learn as well. So, and what we want, let's have a look at this. So it's a little bit hidden, but it's one of those overflow things. So there's a box missing here. And now there's also a very long number here. And you have a strange line break here because the number is so long. And now what you're seeing here is a system that can tell us, okay, I was expecting this to actually look like this. Where's the button here? I'm missing the button here. And also says, this is weird. So it shouldn't break like this. I've never seen that, at least. And it would say, oh, here's, I mean, it's a little bit overlaid. So, but it would say, oh, the spacing here just isn't right. And suppose you could have that. I mean, some system that could tell you that's how I think it should look like. And then you can still do the comparison and say, oh, it's off by that many pixels. So this thing, just by counting the number of pink pixels, you would see this just doesn't look right. And this is actually from the system, so it might eventually work. Now something that's error-free. So it's again layered on top of each other. So the pink ones are the ones that don't quite match. And I mean, from the prediction to what we really see. And you have some pixels off here, just weird, not quite sure why. But it would say, yeah, this thing changes. I mean, it depends. So it could be this, it could be that. It's just any number. It might be different, but not a big thing here. And this thing, it changes a lot. So I'm not quite sure how this should look like, but I'm pretty sure this number should be here. And I'm pretty sure, so this same number more or less. And I'm pretty sure that something down here is also not too long, and it looks like this. So just pretty much like a human being would be able to do that. Yeah, so maybe you can do that. And of course, we can do that. So what's the approach? So we train that autoencoder on mainly correct screenshots. I will show that. And then if you do that, that autoencoder will be able to create those correct screenshots with a small error. That means very well. So that's our hope. And now after the training, we feed in all kinds of screenshots. And if the error is small, we say, oh, that's probably a good thing. So that's a good screenshot, like we saw before. That's probably not broken. Small error, probably not broken. And big error might be broken. And we can look at the screenshots, we as human beings, with a high error and see, is it really broken, or is it something, I don't know, something weird? Or is it maybe a complete new feature, and we see that, and then it's all fine. Okay, so again, the autoencoder. So the input, as I said, it now gets specific. So this is a real implementation, so I'm getting more specific. So we are using screenshots of the application. We scale them down to 256 times 256, and we use grayscale. That's just to take off a little bit from the compute load, because it's unfortunately it's expensive to train that. Obviously, if I lose the color, then I can't tell if the color is off. But this thing would train just as well if you were using color. So I'm just doing it to make it a little bit easier for the machine to learn. And so how do I implement this thing? So it's a neural network. It's convolutional layers. If you know what that is, if you don't worry. And we just have 8 neurons in the middle. So that means this thing here is around 65,000 values, and we compress that to 8. And then from that, we have to decompress it, and it should look like pretty much the same for normal images. And that is a very, very hard task to do. It's very, very hard to learn for a neural network. Just 8 neurons, just 8 values. So, and then as before, what we're trying to optimize for is the number of matching pixels. So that's what we saw before. And you also can give this as an objective to a machine learning task, which is quite nice. You say, try to make this as low as possible. There you have the data, go. And then it runs on GPU, unfortunately. On CPU wouldn't train, would take too long. And then after a while, yeah, we can have a look. Maybe it works. And we will have a look at the training part in a minute or two. First, I'm looking at my clock here. Maybe I shouldn't go into too much detail. You can look at, I will provide all the sources if you're really interested. I have running code that runs without installation. So we're not diving too deep into this. This is just the first part. So just have a look. So we're feeding in the data, 256 times 256. And now all these things, we're not going into detail. We're going down here, and the information gets compressed and compressed and compressed by certain so-called convolutional operations, and then also downsampling. And then eventually we have it down to just 8 numbers, as I said. And directly before that, where is it? This one, I guess. No, this one. We also, just to have a visualization a little bit later, we also have a certain layer which I can directly connect to, that will give me an 8x8 image that will at least give me an impression of how a complex image is represented using that encoder layer or encoder partner. As I said, I'm skipping this. It might be interesting. I mean, if this was a new network conference, this would be the most interesting part. But as we are testing, I'm just going over it briefly. Now, the decoder part, which comes after the dense representation. Maybe I'm going back a few slides. So this was this part I showed before. Now this thing, the encoder turned it into this compressed representation of just 8 values. This again is fed into the decoder, and now we're looking at the decoder. And the decoder, it starts by just 8 values, and now we're doing a reverse order of operations. So the convolution, there's a transposed convolution, which also is a convolution, but transposed, well, no details here. And then eventually we are regenerating 256 by 256 pixels, because we need to recreate the input exactly. So if not even the resolution matches, then there's no way to achieve that. So we have to make sure that the input and output match here. And this thing, if you ask, where's it coming from? I mean, I just made this up. And there's, I think in the meantime, I changed this a little bit, and it trains a little bit better. So it's a lot of like intuition, looking what other people do. There's no clear rules. It's like the early age of science. We're all just experimenting, and this goes for everyone. Like even the stars, they're all just experimenting and reading papers of what the others do. So that's what I did. This is more or less random what I did here. So, I mean, random is the exact numbers here, the exact number of layers. Just need to make sure I can recreate this input. So, okay. Now, as I said, directly before the 8x8, directly before the 8 values representing the bottleneck, I have a certain layer which I can directly connect to. And this is the output from that layer. And the output has a resolution of 8x8. It's still an image. And this thing here, this thing down here, is a representation of this. I mean, I put this into the encoder and I get this. Obviously, it doesn't make any sense. I'm just showing to us, I mean, how much this is compressed. And then you also have to imagine that from this 8x8, I just take 8. So our whole compression would boil down to one of those rows. I mean, obviously, it's trying to put all the knowledge in one of those rows, but just imagine, it's very hard to do that. You can also see some similarities. I mean, you don't know what it means, but this thing, this block repeats in most of them, but not this one. Maybe if you got really intimidated with your neural networks, you would see, oh, this is because they're all broken, and this one is not. Maybe that's it. And then I think you can see a lot of similarities, which is quite interesting. This is just to get a little bit of intuition. It's not important for this thing to work. It's just important for us to see how hard the task is, and there might be actually be patterns that this thing can reproduce. Now, as I said, bottlenecks only has 8 values. It's called undercomplete, like extremely undercomplete, because the input is much larger. There are also overcomplete autoencoders, but this is not our topic. And it has linear activation, just for the people who understand the neural network part. It means they just output some values. So all kinds of values, the whole range. Now, how does the training work? I said it's trained. So we're training on the golden master. That means we have a state of the application that is supposed to be correct. We assume that's correct because that's the application we were shipping last, and that's what we're training on. And we're feeding in input and output. So we assume that it's mostly correct before the change. So we also have something that we can validate to. So we are saying, okay, now we made a change, a new release. And in our case, it mostly contains regressions. So there should be a lot of errors in it. So we're using this, and we are testing against this. Okay, so that's the setup. And now our hope is that the autoencoder, which is trained on this training set, can learn how an application should actually look like. This is a curve that, if you're familiar with it, you will read it immediately, but probably you're not. The blue line is how this trains over time. So we need to do this iteratively. That's the way it works. And now you see that for the known testing data, it goes, on average, it goes up to over 99% of being correct, which is very good. But now the orange one is the error for unknown data, which is significantly lower, which is also good, because that means for broken things, it will give us different scores than for things that are not broken. So this gap here is actually very important for us. If there weren't a gap like this, then it wouldn't work. And also, if this didn't go up like to 99%, or at least to a very, very high level, you also would see, it doesn't work, but it does work. So it should be quite nice. This thing is for all the training data to see what is the, like, how many of the pixels were recreated correctly for the known data, for the known screenshots. And you're just counting the numbers of screenshots here. So we have 45 here. So most are around 99%. And then some are significantly lower. That might be because they look weird or they're actually broken. It's possible. So it could be that part of the application looks strange because there's something weird in it. It might be broken or it's just different. You could not tell without looking at the images. So this is what you get after training. And on the left, as I said, you might see weird things. And now we are doing it for the new release. And the new release, you see represented as those red bars here. So they are much less samples here, unfortunately. So we have a lot of them here of the known to be good application, but the red ones we don't know. So this is after the change. You made a change, and these ones are the ones that the autoencoder cannot reproduce well. So they might be broken. So they look really different from what you had before. And now you again set a threshold and you say, okay, everything left to that, I think that might be something worth being inspected. I should look at everything that's left to that. And we set this threshold arbitrarily. You could also move it over here, to this one, and then you would just look at these. Probably you would have it left to this big spiky thing here, but the rest, it's up to you. So you could make it a little bit more sensitive, and then you would probably look at a lot of screenshots that are just fine. Or you can make it a little bit more, less sensitive, and then probably most of the stuff you will look at the left here will be broken. Let's do that. So this is all the stuff that's on the left. Up here, you see the real thing, what I fed into the thing. This is the score. So 89% of the pixels are recreated correctly, which seems like a lot, but as I said, most of them are white anyway. So this is the recreation, but you see, okay, it's so used to seeing a button here on the right. So it will recreate this thing with a button, which is weird, right? So that's where the big difference comes from. It says, where's the button here? I need that button. Same here, same here, same here. You see the button is lost many times. And also this thing here, you have this overflow here on that box on the right. And it's gone here because it has never seen that. It's not able to reproduce this thing. So this also counts for pretty high error, because not only is the box here, is it not looking right, you also have never seen that overflow, and you think, okay, it should look like this. And it's quite nice because it actually works. So for the example, you will find a lot of broken things, given that you actually have something that's broken like this. This thing would only, like an overflow, would only account for a few pixels, but it would still be noticeable. So coming to the conclusion already. So this is just something I did as an experiment. So it's not a product. It's not something you can download somewhere and then you try it on your own thing. But it could be. Maybe you're inspired by that. I'm not someone who can build a product. That's just not what I do. But maybe you can, and then I would find that nice. For the test part, the red ones, most of them were actually incorrect. So I tested this whole thing with a lot of screenshots that contained a lot of errors. So that's typically not the case. And we chose a very, very low threshold because we knew that because we have few correct screenshots. Oh yeah, few correct screenshots in the test set, so that made sense. And And I also try to check the whole thing, to validate the idea on a change that doesn't break a lot. So I'm not quite sure if it still works, but we're still not on a human level. So we can recognize a long number and we can say, yeah, that long number might make sense because it's, I don't know, money, or maybe not because we don't have that large amount of money. So a machine will not know that because the machine doesn't have the world knowledge we have. In overflows, we just see that. We are not even thinking. So visual system just sees that. You look at the screen and you see, okay, there's an overflow here. Or something's broken. It just looks off or ugly. But system could not find if there should be a button and it's just not there. I mean, if it's permanently missing. I mean, if you think about it and then you say, oh, in order to make this functional for a human being, there needs to be a button. It has never been there, maybe. We can see that as human beings, but certainly not a machine. So what are the open questions? How to actually get to good training data. So I created a lot of data that I trained the autoencoder on. How do you even create that data? So you would need to have a system that could click through your whole application in a meaningful way. And that sounds like easy, just click on the buttons, then things will happen. But often you need to fill in a form in a certain way to be able to go to the next screen. You might not even be able to tell which button is the right one to click. It could be a machine learning problem all in itself. I came up with an approach that does some sort of reinforcement learning where a system learns how to use your application, but it's not trivially technically. So it would do a lot of experiments, try to find out things, but it's not so easy, mainly because each experiment would take a long time. Just clicking on the application, it unfortunately takes a long time. Right now, I'm using random events from a given set of known actions. So for each page in the application, I know what are the reasonable actions and what you can do to make them fire, maybe a sequence of things. And then this thing picks random values from a known range of values that I've given it up front. So it's a lot of manual work and then some random stuff. It would be great just all by itself to have a system that clicks through your application and takes screenshots. I would buy. I don't think it exists. And then even more radical, what would you even use for training? How would you tell a new feature from a bug? So there's a new button because that's supposed to be there, because that's a new feature. Or maybe the layout is broken. How would you tell the difference? And that's especially hard for major release. Maybe not a minor release where you just fix a few things. For major release, often it's very hard for a human, even as a user, to say, should this button be there? Is it just a major change or is it broken? Sometimes it's hard. As I said, there's a reference implementation. It's done using Colab notebooks and TensorFlow. That means this thing just runs on Google servers. If you click on it, no installation needed. You need to understand what it does, though. And that's the project that this is all based on. So it's all free. Do what you want with it. And there are other people using the same approach. So it's not a weird idea to do that. So the Airbus people building parts of the ISS, they use the same approach using the autoencoder that reconstructs a signal from the ISS. And if it cannot be reconstructed well, like our thing, then it might say maybe there's a problem with the ISS or anything. We have to look into it. So second example, if you want to play with stuff like that, it's very nice to play with it. It does it for heart ECG signals. I'm not quite sure what they really are, but you measure something about the heart. Also nice. And that's it exactly. My timer rings now on the last slide. That's pretty good. That's it. So questions. Oh, wait. If you want to have the slides that's a link. You just have to, it's a bit.ly link, so you can just type it in, or we'll put it in the chat, I guess. If you want to stay in, so all the slides are there, and if you want to stay in contact, I'm on Twitter and LinkedIn and all that stuff. You get in the slides now. Yes, are there any questions?
All right. First of all, thank you so much for the talk. Really enjoyed it. So we have one question right now. I guess it's a summary. So the summary is from Andreas. We train a neural network to be able to reconstruct correct screenshots from a compressed state. And then we compress unknown screenshots and reconstruct them with the trained neural network. And then we compare them against their uncompressed state. If there's little difference, the unknown screenshot was probably the correct looking one. Somewhat, if not, like something is broken. Is this the correct summary?
Absolutely correct. And I'm just wondering, why did I give a 40-minute talk about that? Because Andreas really summarized it in a very, very nice way. That's exactly what we're doing. So yes. So obviously you understand what we're doing. And I'm a little bit irritated that's actually possible to write it in one sentence. But yeah, that's correct. It's just right.
Yeah. So, I mean, there's more to it than just those few words. I guess, like, if you have no idea of neural networks, so I think you gave a great introduction, like an overview to all the things. So we have another question. So how can I train my model if I have different scale images? For example, I have different scales for buttons, 32 times 8, 122 times 64, and so on. Should I care about the scale in this case?
Oh yeah, Pavel. No, so you will just take a screenshot, not of the, at least maybe I'm not understanding it right. You have scales for buttons. You would not test for the single button, but you would test for the whole screen that you're testing. So you have a screen that you have buttons on that. And if they differ in size, if they're sometimes like that and sometimes like that, you would, at least that would be my approach, trust the neural network to learn that sometimes they look like this. And maybe the neural network, it can even detect what makes that difference. I mean, when is the button this size and when is the button that size? So with training neural networks, it's always like how much information you put into the system. And if you rescale, or I don't know, do something with the input, the neural network can never like get to superhuman level, which sometimes it does if you don't put too much of your information, which might be flawed. So short answer to Pavel would be no, don't. It's just you put it in there as it is, and then you hope that the system, I like this plot, maybe I'm the only one in the world who likes this plot, but maybe in one of those values, this thing will learn, okay, this should be a big button and this should be, I don't know, it's related to this, and that's our hope. So you won't.
Yeah. All right. So I will just put your link, I think, into the chat. There was one question about the repository, but I think it's answered right now.
Where it is? Yeah, I think it's in the slides. I can
yeah, like he removed his question, I think. So I think it's a link.
I removed it? Oh, sorry.
Yeah, perfect.
I didn't mean to.
No, like the question was removed. It's fine. All right. So are there any more questions right now?
Post the
yeah, we can just post like everything in there.
Just post everything. I mean, it's in the slides, but maybe it's tough to go through that. Yeah. So
Yeah.
If there are no more questions, let me say, if you want to use it, if you want to do anything with it, if you have questions, ask me. As I said, I'm not in the product business. So if you want to do something, if you want to work on that, if you want to try that, just let me know. So we're not competitors, so we're all on the same side.
We all want to make testing better, I guess.
Yes, exactly. Yes, that's my approach.
That's a nice one. All right. Thank you so much, and thank you all for joining the talk. The session will close shortly. So again, it was a nice talk. Really, really nice to have you here. It was awesome. And see you all in the next one. And have a nice rest of the day, I guess. Enjoy.
Yeah, thank you so much. Have a nice day.
Bye, everyone. All right, and we are off.